So I'm going to talk a little bit about the basics and then the technology, and we have another member of our staff, our executive team, that's going to be talking more about the marketing, going to market. So I'm going to go through the background, then we'll do the engineering aspect, the validation engineering aspect, and then we'll talk more about commercialization. So kind of our first two speakers laid out some of the issues, and just to summarize, so you have this dichotomy or conflict between what can be affordable versus what is responsible, and then you have this massive problem. If you don't do anything, then all the economics go off the cliff. So when do you do it, and who pays the bill? So one way around that is come up with a breakthrough technology that is actually vastly better economically and perfectly clean. I mean, not talking about minor, it's perfectly clean. So you can't get anything better. I mean, even nuclear has nuclear waste. So just like an ABC tutorial, just going through the fundamentals of what we do. So this technology-oriented had its origins quite a while ago, and it's been, I think we spent something like $110 million, enormous amount of time. I can't even tell you the time. It goes very quickly, and we're having so much fun that we don't even realize it, but this is a massive amount of work for a small company. Most companies have it really easy. They just make a little incremental change or write a little app for a phone and go public in a couple months. This is a little bit. This is a heavy lifting program, but the implications are, I think, more profound than any company has ever done in history. And of course I'm biased, but I think you'll find that to be the case. So this started out when I was a student at MIT, and Kurt mentioned he crossed paths with us a while back, and fundamentally there's a big issue in the beginning of the 20th century, and it was actually a crisis. Why is the atom stable? Like the electron keeps moving around in a circle, meaning like if you're skating and you try and go turn, you have to apply a force. Whenever you apply a force, there's acceleration. And according to classical physical laws, whenever there's an acceleration, then charged particles like electrons give off light. They radiate. So here you have the atom, the electrons going around constantly accelerating because it keeps changing its direction. The force is the attraction between the positive proton, the nucleus, and the negative electron. Makes it go around in a circle. But it's not giving off light. So the way that was dealt with is they just said, okay, it doesn't give off light, so we'll just say those are the energy levels. That's it. That's the energy level. It doesn't have any energy level lower, and we'll just define that as like a thing of nature. Well, I mean, let's face it, hydrogen's in everything, and even our bodies, and it's not in that energy state. So you can't just define it as a fact of nature. And it doesn't come about in terms of physical principles, which is kind of, it's a shortcoming, because you can't predict anything new if you don't understand how the basic system works. So this was based on some free electron laser theory that my professor worked on. It basically explained from physical principles, things you can directly measure, laws of nature, why charged particles radiated. And then I just said the converse. Well, if we know how they radiate, why is it, can we apply that and determine why it is that the electron doesn't radiate in the atom? And when you actually solve that problem using physical laws, which no one did before, they just said, well, we'll just define it and make up math, and from there on we'll just curve fit everything. So the standard model now has like 26 adjustable parameters, purely arbitrarily match the data. It's like looking up in the back of the book where they have the answers. And you look it up and say, oh, that's the answer, and you just put it down on your test. That's the way things are done. So this actually was a derivation of what the structure of the electron is, and therefrom calculating everything from subatomic particle masses to predicting the acceleration of the cosmos before it was observed. It's absolutely perfect on everything it's predicted and solved so far. And when you get something that matches 1 followed by 85 zeros in terms of the scale it covers, it's how improbable is it? I mean, how improbable that it's wrong. I mean, it can't be wrong when you get everything. You saw everything from particle masses to cosmology. So I'm absolutely certain the theory, based on physical laws that you can directly test, is correct. And it predicts that you can have more stable states of the hydrogen atom. So that's a big benefit of having a fundamental theory. It's a major technology, solves major problems. And there's a lot of clues that this is going on. I mean, you'd say, well, does it happen in nature? It seems like we ought to observe it somewhere. It's happening everywhere. I'll go through it. It's in a huge amount of evidence out there. So A, astrophysics. The sun is comprised of essentially all hydrogen. And conventionally, it's thought that all the power is being generated from fusion in the center. And then it takes massive amount of time for that energy to travel through the sun and then be emanated from the surface. But then there's very transient events, not like on century type time scale, but on very transient, where you have flares and very active coronal events. That's the gas around the sun. And those regions can emit the entire power of the sun. So, how can that be? I mean, that's a lot of power coming from very, very rarefied gas around the sun. And there's it's very, very, very low pressure. So how can you concentrate that much power in this very, very thin gas? I mean, it's like, it takes very sensitive instruments to even measure it because the vacuum is so great. It's like vacuum, it's so thin. Well, it turns out there's a couple clues. One is it's making ions that make it look like it's 2 million degrees, but the surface is like 100 times colder. So how can the surface be heating it up that hot when it's up against cold space? It's basically as cold as you can get. So it's like somehow the frying pan is like 100 times hotter than a stove. But they're big numbers. I mean, it's very hot. Everything on the sun is very hot, you can imagine. So the surface is hot, but then the gas around it appears to be extraordinarily hot. There's no real mechanism for that to happen. And in fact, there's other evidence that it's not that hot at all. There's still molecules and things in the solar corona that would say it's not hot. It's much cooler than the surface. The explanation for that is that the process whereby hydrogen forms this hydrino, more stable form of hydrogen, emits soft X-ray light, and it'll make those ions. So you can have very, very relatively cold temperatures. In other words, the ions aren't being created thermally, they're being created by absorption of very high energy light produced by hydrogen going to this new state we call hydrino state. So this occurs in the sun. This process occurs in the sun based on that and other evidence. You can see it occurring in white dwarf stars. There's certain spectral cutoffs of a very characteristic signature that this process emits. And those bands are in those stars, and it's the same bands we see in the lab. It's also the same bands that are coming from interstellar regions of space where they say there's a mass there that can't absorb or emit light. They call that dark matter. So dark matter isn't rare. It makes up about 100 times more than the mass that we can see. So we can look out in space and we see stars, we see galaxies. But if you look at it from a gravitational perspective, it's a very, very small amount of the matter that we can actually see based on gravity. And I'll show you an example of that. So if you look, this is real. I mean, there is something called dark matter. You can map it throughout the cosmos. It maps about the same distribution as ordinary matter, and this is it. This is the distribution of dark matter in the universe. So it's a very, very well characterized phenomenon that there's this enormous amount of mass and no one can identify what it is. this is an image of dark matter. And you can see there's nothing there. But you say, well, how do I know it's there? It's because you can tell that these galaxies are being lensed from some other part of the universe. You can change the angle of the telescope, and these will move. And then based on they have a very distorted shape. I mean, they get like this elliptic. It's distorted. And they move it, and it'll change its shape, it'll change its position. So it's being gravitationally lensed from somewhere else. There's some enormous amount of gravity here in this dark ring that isn't absorbing or emitting light like all this other matter, which you can see here, which is basically all hydrogen. And what we're saying is, if you look at the spectrum coming from these regions where it's forming, you get this continuous band. You see how there's a continuous hump here versus these very sharp lines? Typically, matter is identified by very, very sharp spectral lines, which are characteristic of and identify a certain element. This can be totally missed because this energy, and it was missed, this energy, or this spectrum is in an energy region where very, very few people have this instrumentation. It's very, very rare. And it's a band. And unless it's very, very intense, you would just think it's some artifact of background. But when you get a cell like this making 1,000,000 watts, and there's essentially no visible or infrared light, like longer wavelength lights, there's just this high energy light, it's actually striking that you'd even have something that emit that kind of light. And it's the same light that's being observed from all over the cosmos. It's characteristic of and identifies this new hydrogen, this hydrino form, and it's something that requires instrumentation, is in a region that no one really pays attention to. And they don't pay attention to it because this light can't even go through a millimeter of air. You have to use vacuum connections. You can't use windows. You have to actually have a hole right into the reactor, directly into the spectrometer, and pump at enormously high rates. So there's a huge pressure gradient so the spectrometer can see it and the source can make it. So it's not an easy thing to do, and it's been completely overlooked. And this is what we've sought, and we've proven that this spectrum is created by this reaction. So this is a signature that is characteristic of dark matter, which makes up almost all the mass of the universe, and verifies the product of our reaction. So the two are linked. Dark matter, product of the sun cell. They're the same thing. And it has a characteristic that it's extraordinarily stable, lighter the air, and vents the space. So it's absolutely the perfect product. No chemical reactivity. Perfect product. Doesn't even absorb or emit light. Perfect product for a power process. Hydrogen is the most abundant element in the universe by huge factors. Water covers more than 80% of the surface of the planet, some places a mile deep, so the fuel is ubiquitous. And it's an enormous amount of energy per hydrogen. 200 or 300 times that of, on average, of burning hydrogen. And what we've, the breakthrough that is enabling this finally to become commercialized, as Kurt was saying, we've worked on this a long time. It took a lot of theory, took massive numbers of what we call embodiments or approaches to make this reaction. The breakthrough came in November 2013, where we established something called an arc plasma state. That's where you have a very, very high current, and the energy of the system actually goes lower the higher the current. It's the opposite of Ohm's law. Like a toaster, the more current you put through it, you've got to put more voltage through it. This is opposite state of matter. So plasma is like the fourth state of matter. You have solid, liquid, gas, plasma. Plasma can be a ohmic type plasma and an arc plasma type. That arc plasma creates massive kinetics. And since we had that breakthrough in November, we're this close. We're within a 6-month time frame, as you'll hear from the engineering firms, of getting out in field trials. We stay on course. So it's happening very, very fast. It took an enormous amount of theory, took an enormous amount of effort and different approaches until we got to the point where we have a breakthrough in terms of not only high energy. We always knew the thing worked, the process worked, but it's getting massive kinetics so it could be commercialized. But the product and the basic phenomena has been again and again proven out with our analytical tests and our spectroscopic tests. I'm going to go into more of that. We even have more details on that in terms of making absolute affirmation of how much power we're getting and confirming the fundamentals of the process. So B is for black body light output. So we're going to convert that high energy light into something called black body light. And I'll show you that. So here's a reaction. It's, and you say, well, how much power is that? It's a lot. And then, and Peter's going to speak, Peter Jansen, the professor from Bucknell, is going to speak to some of the validation. One of the validations was to actually take a spectrometer and measure how much optical power that was. So let me go back and show that one more time. So there's two characteristics of this. One is huge amount of power, and the other is it's very transient. That's high-speed photography. That's about 1,000th of a second. And the goal of the engineering is if you could fire that 1,000 times per second, then you would have continuous power output, and you'd have something that's really, really interesting as a power source. Then the third question would be, can you convert that light directly into electricity? You can't convert that light with conventional photovoltaics as they exist in that today. There's something called gallium nitride technology that could potentially go that high energy region and do direct conversion, and we have a program to do that. But in the meantime, we're taking advantage of traditional photovoltaic cells. So we're going to take that power and we're going to heat up a refractory material. These are things like carbon, tungsten. I'll give you an idea of what a refractory material. The tungsten filament in an incandescent light bulb is what you'd call a refractory material. It gets so hot, it emits white light. And that white light can be converted into electricity. And those types of materials, when they're that hot, they emit enormous amount of power. So this dome on the cell, that I'll show more in detail, would get to 3,000 degrees Kelvin. At that point, it would be emitting almost 5 million watts per square meter. We can also push it up to 3,500 Kelvin as we advance the technology. That would put it at over 8 million watts, almost 9 million watts per square meter. Enormous amount of power flow. And they're photovoltaic cells that will handle super, super high concentration, 1,000 times more the intensity of sun on the Earth's surface, that can convert that into electricity. And that's basically the technology that we're harnessing. So then the question is, so I showed that blast. Obviously, if it's 1,000th of a second, you want to fire it 1,000 times a second and get continuous light. But how much power is in that pulse? So what you're seeing is different stitched together spectra from 3 spectrometers. And what we did is we had the work we did back in May, somewhere between May and June, in terms of validation reports, which are now available on our webpage, except for one of the experts who did thermal modeling. He's the best thermal modeler I know of in my entire career. He works for a national lab, so he's got some other conflicts. We didn't put his up there, but all the other ones are up there. And fundamentally, that model was looking at quantifying how much power we were getting out from an earlier sun cell generation. And the other test we did was a commercial calorimeter, and the third test was direct optical spectroscopy. So those techniques and those validations are on our webpage. And there's another very good resource is on June 28th. We did a live demonstration of the optical spectroscopy power measurement, the commercial calorimetric measurement, and the power measurement based on the water coolant temperature rise with time. So there's a coolant loop that takes power away from the cell, just like a heat exchanger would take power away from a boiler in a power plant, like a coal plant or gas plant, a coal plant in terms of a central power generation Rankine type cycle, and it goes into a steam generator and then into a steam turbine. So it's the same kind of idea. You take away the heat in a coolant loop and measuring the temperature rise due to the power generated in the cell. All those were showing megawatt scale powers. But then there was a question that we had external to the company in terms of the optical, because optical is absolutely infallible. Basically, you're taking a light source and you're measuring how much power that light source is outputting in the spectrometer. So the spectrometer is going to have some reading response to that light source. And if you know the power of that light source and you look at what the intensity reading is of the spectrometer, you can basically calibrate it. So then you get another unknown light source and you make that incident on your spectrometer and look at the output. You can now measure from that calibration how much that light, the new unknown light source, output. So we use something called a halogen lamp, which is a calibration source from the National Institutes of Standards and Technology. And it covered a certain spectral range. It didn't cover the range that was where most of our light was emitted, and that was one of the criticisms. You can take industry data, or in this case, scientific instrumentation manufacturers' data, and you can interpolate, that is, extend the halogen lamp down to the region that we were measuring. But again, it's interpolation. It wasn't a direct calibration. It was extension of the calibration we used. So we bought a very expensive instrument, very, very hard to get in terms, it took 6 months to get it, and we went back and we calibrated not only the longer wavelengths, but the shorter wavelengths as well. So we have an absolute, infallible, direct calibration of the region of interest. And it actually showed more power. And so here's the numbers from that calibration. So that blast you saw, which we can do on demand, that blast is showing 1.267 megawatt average power over that blast. And the peak where it whites out is 4.97 megawatts. So it's about 5 million watts of light. So and you're going to see that ties into the peak powers out of this sun cell that we have in our validation reports, and then Peter's going to address. So that's a big deal. So we have a direct measurement, an infallible measurement of massive megawatt type power out of extraordinarily small volume. There's no primary power source that can make power that intense and that high density. So to make that go at 1,000 times a second, we need to have some engineered systems. And you can back, we did a demonstration on January 28th of this year. It's actually a 2-year anniversary of when I first showed the fundamental phenomena. And that addressed many of the different approaches, well, some of the highlights of the approaches we took, looking at powder injection, looking pelletization, and using pneumatic injector, and all kinds of different ways of igniting that fuel at 1,000 times a second. This is really, really elegant, what we have now. And it took a lot of work. But it has 6 fundamental systems. So first of all, and all this stuff is technology that converged. This would not have been possible in most cases 10 years ago. If you look at most of these systems, maybe even 5 years ago. But it's all industry-proven, standard parts, no new technology required from us. It's the way we package it. And it makes it into a new invention that's quite remarkable. So we have a startup. So we, as I was saying, to get this arc plasma state, we have to have a highly electrically conductive medium. And to conduct current, because the process involves, that is the process of hydrogen atom to hydrino atom form of hydrogen, or dark matter form of hydrogen, requires an energy transfer to an acceptor. And we call that a catalyst. And that energy is a lot. And it ionizes, and that's actually the energy match between the hydrogen atom and the acceptor. It has to be an energy match, and that energy is high enough to ionize anything. I mean, by definition, the acceptor has to ionize as a consequence of accepting that energy, and that is, in fact, the catalyst reaction, is an ionization reaction. So we have energy transfer, something gets ionized. Well, those ions build up and they're charged. Like you're in well, as winter approaches, you'll find out very shortly that as you shuffle across the rug and you touch something, you get a shock because you build up charge on your body. And it stops. It's limiting because as the charge builds up, it's harder to build up more charge, and that's good, or else your arm would be like fried like a tinder or something. So, but in our case, it's not good because as the charge builds up, it changes the energy levels and the reaction slows down to a very slow rate. So this arc plasma takes care of that. It basically mitigates that charge buildup, and we get massive kinetics, as you saw, massive. So we need the highly conductive medium, and we use silver. Has no reactivity. It's extraordinarily conductive. It's got a reasonable melting point. There's a lot of characteristics about silver that makes it absolutely the perfect medium. So we have an inductively coupled heater that has something called IGBTs. Those are electronic components. Again, that was more recent innovations. It emits radio frequency, and then the radio frequency penetrates into the or heats up the cell and melts the silver. So to get that kind of power density with a heater is really essentially impossible without this technology. So that was a good convergence of technologies in terms of enablement. The next thing is you need to have a source of hydrogen, and you need to inject the silver and the catalyst. And that was solved by using an electromagnetic pump. These things are 60 years maintenance-free, nuclear industry, chemical industry. Again, something that was essential that we could use. It's proven technology. You need an ignition system. So it's very low voltage. It's like a flashlight battery type of voltage, but very high current. Again, supercaps, a relatively new innovation in storage, another convergence of technology. The whole system then makes enormously high power, enormously hot plasma temperature, and that heats up a black body radiator. And there's been a lot of work in terms of trying to make black body radiators illuminate photovoltaic cells. It's called thermal photovoltaic technology. Never been a power source with high enough power density until now to enable that. But we can use all that. We can use the refractory materials and the concentrator photovoltaic. So we got a black body radiator, goes extremely high temperature. So it's basically a huge light bulb that has thousands of times the surface area, conventional incandescent light bulb, that illuminates concentrator photovoltaic cells, and then that's converted into electricity. Then there's a fuel recovery and thermal management system to recycle fuel. So it's a closed system, and it can run indefinitely. So that's basically the parts. So this is what the engineering drawings look like. So we have looks like we have PV module, and then this should be here. There's a black body radiator here. That's this guy. So this is the illuminates. And then there's a gap here, a very small gap, and the photovoltaic goes around that. And the whole thing is in a pressure vessel. That's this bell jar. And it bolts down here on this base plate, and everything goes through the base plate, all the mechanisms. The pull power in and out and control and the like. So this is pressurized about 10 atmospheres, because when this is at temperature, the silver vapor pressure is about 10 atmospheres, so there's no net pressure. And extraordinarily safe, no net pressure. And this outer vessel is, so it's about the pressure of a bike tire. But it has everything here that's under pressure in terms of the outside world sees is cold. It's got cooling plates around the perimeter, and they keep it basically close to room temperature. So this thing is extremely, extremely safe. It's got a silver and catalyst injection system. That's these tubes. It's got an electromagnetic pump, as I was saying, that pumps the molten silver, injects it. And this is a new innovation. There's no electrodes. Typically we have an ignition system comprising electrodes, but we have two metal streams, one from each of these pumps, and when they intersect, both of these have applied voltage, and when the two intersect, bam, you get the ignition. So what you saw before, that bam, that was that flash of light, that was from ignition from electrodes that held a fuel pellet, We electrified those electrodes. No electrodes. This is a dual molten injection system that supplies the pulse of electrical current to trigger the reaction and give you the massive kinetics. So this is a demonstration we did at Columbia Technologies on July 20th. And so this is a prior generation cell. So that little whine in the background was the alarm from the glove box. This is like human size. It's big, and then you hear some snapping and clicking in the background. That was the glove box trying to adjust the pressure because there's such massive amount of heat released in there. It set off the pressure alarm, and the pumps and systems and valves couldn't keep up with the surge in pressure. So that's human size, and that plasma, it was hotter than the surface of the sun. When that event occurs and we put a spectrometer on it, it actually shows black body radiation that's hotter than the surface of the sun. I mean, that is an enormous amount of power. So that's good. We can make a lot of power.
Could you explain just what we were seeing in the video? So that's actually the injection of the silver.
Yeah, what you're seeing. Let me go back here. Yeah, I'll take some questions at the end so we can keep rolling, but hopefully I'll address everybody's questions through the talk. But there's so many talks I could give. That's the let me go back. Well, let's look at this part. So here's looking down at the top. This might give you a little more information. So here's the two tungsten electrodes, or quarter-inch. They're very thick tungsten. And tungsten has the highest melting point of anything, any metal. And what we're doing is we're injecting the molten silver up between those two, and when it goes up through, it gets a current, it gets ignited, and you get the reaction. Now it's off, and one thing you can say is it's still going. I mean, I'm going to talk more about this, but once the ignition system can go off, and it can still go. Because remember, we just need to have highly conductive matrix. The other thing, so it's still going. It's cooling down it should cool down like a light bulb. I mean, it's so hot, it's melting tungsten. That is hotter than an incandescent light bulb. What happens when you turn off an incandescent light bulb? It goes cold immediately. There's no light. This thing's continuing to emit the light. The other thing is, you can see the electrode's gone. It's completely melted, and it's not only melted, we can use a spectrometer. We see tungsten ions in the plasma, meaning it actually vaporized it. Like there's nothing known. Primary energy source will melt tungsten like butter and vaporize it. That's why I thought that was very cool. I thought, wow, everybody's going to know there's a new primary energy source because there's nothing else that can do that. But that did impress some other industry types. They want to see something run long duration. That's not good to have it just have your cell vaporize. Because this is what it looks like afterwards. And you can see here, this is looking inside. So this is all gone, the whole thing. And then this electrode, what's left of it, this is the cooling bus bar. It's just a little stub there. So it used to be a tungsten quarter-inch thick, like maybe an inch wide, or excuse me, 3/4 inch wide, and maybe 2 or 3 inches long, and it's gone. So that was a problem we had to solve. And this engineering is going to address that issue. So as you can see from the video, the plasma is extremely, extremely powerful. And if you measure the temperature, you can fit it. It'll fit a black body curve of around 6,000 degrees, which the surface of the sun is around 5,600 degrees Kelvin. So it's extremely hot. And we only need to go to 3,000 degrees Kelvin to activate our photovoltaic converter. So we have plenty of power, density, we have plenty of temperature to achieve the operating temperature of the black body radiator to form the emission that we need for the PV to work. So that's the only takeaway. We got a lot of power, and we got enough to make this work. So that means we got enough power to make conversion. Conversion, so I'm going on the C. So Now, Kurt was talking some about solar cells. They're actually discovered, the photovoltaic effect was actually discovered by Becquerel in 1839, same year as Grove invented the hydrogen fuel cell. So anybody that complains about us taking 3 years should go back and look at when photovoltaics was actually discovered. This was discovered, this event, remember I was telling you, in November 2013, so now we're very close to productizing it. So we're actually moving very fast on a historical basis. And we spent, I guess we spent about maybe 10 million since then. And solar cells, there's been about $1 trillion spent. And we get to leverage that, which is a very good thing. The other problem with solar cells is they take a lot of land. Like this is a 100 megawatt, and it takes like 250 acres. So you just basically panel the earth with solar cells. Then you can say, well, I don't want to panel the earth because that's a lot of solar cell. So maybe what I'll do is I'll just panel it with mirrors, because you can't make the sun any more intense. You still have to collect it over the same area, because it's so much power per unit area from the sun, and so much area times so much power per unit area gives you so much power. So you still got to cover 250 acres, but you can use mirrors and then illuminate these concentrator photovoltaics. That's what we're using. So the industry actually developed, very conveniently for us, solar cells that are incredibly, they're incapable of accepting incredible intensity. And the higher intensity is actually much more efficient. Rather than say like 10% or something like a conventional solar cell, these things go up to 42% they're achieving in the field now with the concentration. So they use like 10-meter across mirrors, parabolic mirrors. They concentrate this light into this concentrator cells, which are maybe like the size of a wallet, and it cuts down on the amount of material you have to use, and they're much more efficient. But you still are covering the same amount of land, and it's 250 acres, and you got to buy all this other stuff, like you got to buy the mirrors and the trackers and all that stuff. So it gets kind of complicated. But we're going to use that concentrator. But what we'll do is we'll just put another dome outside of this dome, and that will convert light from our light bulb into electricity. And the light bulb's driven by this Hydrino reaction that ultimately has hydrogen as the fuel source, the hydrogen derived from water. So we have a water-based fuel at huge multiples the energy of burning, driving this thermal photovoltaic application. So we're going to run 1,000 suns. We can probably go to 2,000 suns. And there's actually devices in the lab now running at 10,000 suns. So you can go very, very high concentration. The other advantage we have, that in addition to having a light source to run 24/7, 365, is that we can recycle the light. Like if this light bounces here and it doesn't get converted, we can bounce it back. You can't bounce the light back from a solar panel to the sun. But here we can. We can bounce it back and forth. So we're looking into getting a much more improved efficiency beyond what they can do with triple junctions, which is phenomenal, by recycling light. So it's going to give us some additional efficiency. So we would propose using something like this to replace this. And this would run all the time. So, and you can put this in a car or truck or train or mobile applications, in addition to stationary. So as I was saying, we get really, really super high light, and it's making megawatt type power by an infallible measurement. We can't convert this directly because I'll show you where solar cells are. You see solar cells here, they're saying like 300 and up to like 1800. See how this graph? See, 300 is here. And there's essentially no light in that region. It's all down here in the high energy region. That's pretty remarkable. I mean, I've asked a lot of spectroscopists. No one's ever seen a light source that makes just ultraviolet and extreme ultraviolet and makes no visible or infrared. I mean, think about it. How can something make no heat light and no regular light, but it makes just all high energy light? And it's continuum light too. So So that's another thing that proves that we're doing a type of reaction that no one's seen before, because nothing else emits that kind of light. But in terms of the business of making this into a practical device, so we take this high energy light, it is inside of here, heats it up super, super hot, and then you get this come off. And that can be converted into electricity. So this is a light, this is a intensity versus wavelength. So we convert, this is intensity versus wavelength. So this is all shorter than 300, and then this is all longer. So we can convert this light into that light just by letting it heat up a refractory material. Basically drive a light bulb. And the concentrator photovoltaics are known commercial product. This is one from Azure Space, which is a German company. And it comes with its inlet and outlet for cooling, so it's all prepackaged. So we would just basically make tiles and make a geodesic dome around this black body radiator dome, which is just like 2,000 or 3,000 light bulbs all on one surface. That's the way to think about it. So more details on the design. We kind of covered this. We had the PV module, black body radiator surface. We had the plasma inside here, the injection system, and the electromagnetic pump that's supplying the molten silver and the catalyst stream. And then there's hydrogen that permeates in and out of this surface. So hydrogen permeates through, very permeable to hydrogen at that temperature, and hydrino permeates out. So this is all closed system. And inside there is a constant inventory of the catalyst and the silver. It's all, nothing leaves other than hydrogen in, hydrino out. It's all closed system. So I'm just going through this because I'm going to show you the system actually running. I'm going to show you this guy actually running. So this is more of the details. So it has an inductively coupled heater. And then we have two reservoirs that have the silver that supply the molten silver to the dual injector. Electrode-less, that's important. No electrodes, they can't melt. They're molten metal. And then it's got these sensors. This is a cool thing we added on. So these sensors would have basically, it's like a smoke detector. You know, a radioisotope and a smoke detector, and it puts out like some X-rays, and then they get absorbed. Well, what happens when you have smoke is actually, it's an amorous, and I'll give you more details. 241 isotope. It has alpha particles. They ionize the gas, particularly smoke, when the smoke comes in. And that will cause a current in a circuit, and it'll shunt a current from another circuit, and then sound the alarm. So we're adapting something from like a smoke detector. So we have a source of radiation that would go through here, a particular X-ray, would go through here, and then it's got another detector on the other side. And when the silver level gets up, it blocks those X-rays that go through, and the signal goes down, and we can tell where the level is. And then we can drive wirelessly with control electronics, drive these electromagnetic pumps. So we can keep the level really where we want them. So it can keep the levels adjusted in the two reservoirs as the two dual injectors are shooting in the molten silver. So it's kind of a really cool control system. This is the inductively coupled heater, and this has an actuator that can move it up and down. So we can warm up the cell, get it up to operating temperature, melt the silver, and then drop this down and use it for cooling down here with the electromagnetic pump, so we can use standard materials. All these are standard mechanical joints, no welds, like they use in the nuclear industry, so it's fail-safe. Then it has cooling plates. It has this vacuum vessel, so we can adjust the pressures, no pressure differential on the reaction chamber, makes it very, very safe and resilient. And these are the cooling plates, again, standard technology. We have a electromagnetic pump power supply that will be driven from the power from the photovoltaic converter. We have a battery startup, lithium-ion battery, be satisfactory. Again, known technology. Vacuum pump, just to pump it down to put the gases in initially. We have a water pump for the cooling system for the electromagnetic pump magnets. The electromagnetic pump has permanent magnets, and it has a current that comes from this power supply. It runs a current through this axis. The magnetic field is along the axis coming out of the plane of this diagram. So you have two perpendicular components, electrical current on one, magnetic field on another, and you get a pumping force, it's called a Lorentz force, perpendicular to those two components, and it causes the molten silver to pump.
I do have another question. Where's the water? Where's the water or hydrogen input into this? Do you have an
Here, I'll show
operating
you.
tank?
Yeah, I'm going to show that.
Okay.
So the point of it is with electromagnetic pump, there's no moving parts. Permanent magnet. You just control the current through the pump, and the current drives the pumping. So you can use the sensor for the different levels. So I was saying we had that like a little X-ray sensor, and then that would tell the pump to speed up or slow down so we can keep the constant levels. But all this has no moving parts. Very important. Very, very low maintenance. So this is a cooling water tank for this water pump to circulate water through these cooling jackets, which I'll show you on the electromagnetic pump. We're going to show you on the real cell. So these are just different views of the electromagnetic pump power supply. There's ignition power supply, which is the bank of capacitors, in particular supercapacitors, which again are a nice innovation from the storage industry that we could use. Inductively coupled heater, thank you, metallurgy industry. All this stuff is like, oh great, thanks. That saved us, decades and $1 billion or something. We could just use all this stuff. So it's very good. And then the battery, startup battery, like be $50. It could be really small, just to get enough energy to melt the silver and get the electromagnetic pump, and then it ignites, and then you automatically got instant electricity, and then that's it. So it's got a little, this is what the enclosure looks like, kind of looking through it. So this is the graphical user interface, and then you can disconnect this. And so we're going to run, we're going to use something called H3. It's a gas they use in something called TIG welding systems. It's a mixture of 3% hydrogen, 97% argon. Argon's a component of the atmosphere. It's an inert gas. It can't burn, doesn't have any chemical reactivity. And so we have an argon tank. So we pressurize this up, and then that we don't use that up. That's a non-consumable. The hydrogen, back here. The hydrogen is a consumable. Keep pressing the wrong one. Hold on a second. There. All right, here we go. So hydrogen is a consumable, and we can replenish. Green tank's hydrogen, red tank's argon. This doesn't get used up. This gets consumed, and we can replenish that with electrolysis. Just take water and run a very, very small amount of current through it. I think it's like 0.1% of the energy balance to create the hydrogen to run the process. So there's also an energy consumption with the electromagnetic pump and the ignition system, and then there's some water cooling, pumping, and things like that. All in the parasitic losses are very, very small. They're about 1%. And I'm going to talk about another thing. I should probably do it now in case I forget, which I probably won't forget, but I'm going to say anyhow, so you hear it again. Once the ignition starts and you get it up to high enough temperature, you start to vaporize the silver. That smoke that was coming out from that prior demonstration wasn't smoke. That was vaporized silver. It's basically boiling it off, boiling metal vapor. So you can melt things, right? Like, let me ask you this. Like, let's say you cook up an egg, and you turn on your stove, and you got like a natural gas stove. You ever see the stove like melt like butter and boil the metal away? And that's steel. I mean, that what we're talking about now with like tungsten, that's like 10 times more power, maybe more than that. I mean, in terms of just melting it, because it's got such extraordinarily high melting point. So it tells you there's something very extraordinary going on in terms of that, the power density that you get. So they have so we have this vaporized silver, and the point I wanted to make is we have these parasitic losses. One of them being the ignition system. So you'll see we'll actually turn the ignition system off, and it'll still go, because once you start vaporizing that silver, you have the conductive matrix. So it's actually So and then you can turn the heater off. And in a lot of these experiments, we turn the inductively coupled heater off. So then you're only looking at the electromagnetic pump in terms of parasitic load, which is very small. So the amount of power consumed by the system can be very small. So this is some more views of the sun cell. So C for commercialization. As I was saying, we're going to have Dominic Jones back. He's going to cover this more after we have our engineers speaking and our validator after me. So it's a continuous power source, and we have massive patents. As far as we know, no one else is filing anything. Like incredible amount of intellectual property filed. It's just incredibly comprehensive. It's a non-polluting power source. It has this hydrogen to hydrino, doesn't even burn, doesn't even absorb or emit light, lighter in air, goes out in space. We have water as a fuel. Silver is one of those, you use it in fillings, in teeth. It's incredibly safe. It's a relatively fairly low pressure system, and it's pressurized so that the pressure vessel is actually room temperature, so it's very safe. Very, very cheap capital cost. I'll go over this on a bill of materials, like $50 to $100 per kilowatt, and this is probably very conservative compared to solar. And here's a big differential. Solar is going to be like 100 times more expensive, and it doesn't go 24/7, and it's not deployable. Like you don't have a farm you can cover, say on your car or a bus or train or at your house. So we're going to go to. This is so cheap that it's actually vastly, like 100 times more cost effective to give multiple units than it is even to use urban grid, like just switching power even locally. And it's so cheap, I don't even know if it makes sense to use the heat. We just could use electric because it's so cheap to make electricity. If you use heat, you got to make heat exchangers, and you have to move some working medium, like some fluid around. They call it a coolant, but it actually is the heated up material that goes to another heat exchanger to deliver heat to wherever the load is. So, and we're going to go to no grid connection. This is a purely autonomous power source, autonomous of grid and fuels infrastructure. No grid connection, no utility regulation. You only need underwriters' labs and local electrical permit connection. So extremely low operating cost. We're using the same operating cost I'll show you as solar, because basically the main component is the photovoltaic. It's scalable, and I'll talk about that in a second when I talk about this prototype. And we're going to go initially stationary, something like quick serve restaurants. We'll give them baseload power like 100,000 watts, and then after we prove out the reliability, we'll give them redundancy to mitigate against any interruption, and then we're going to take customers off grid. So we'd be an off grid supplier, and we're timeline-wise, we're field test first half of 2017, commercial launch the second half of 2017, and Dominic's going to go more into that. Just some overview. If any kind of power source as current economics, it's about $1 per watt per year if you run it continuously. So 1 billion watts would be $1 billion in terms of the value of the energy. Capital cost, just averaging it out or weighting it, like $60 a kilowatt, lifespan 20 years. The annual cost of those 20 years then is $3 a kilowatt, dividing A into B. Very competitive relative to existing technology. And typical like coal and things like that are like $1,000 a kilowatt. So it's very, very cost effective. And you have transmission lines, and then you got to pay transmission, distribution, demand charges, and so actually the cost of electricity is more sort of doubled above the generation costs when you consider that. And we're on site, so there's none of those costs. So as I was saying, maintenance cost is going to be 2% of capital costs, which is the benchmark for solar. And then we have, if you take basically our cost of generation is amortized capital cost, and it's like a millicent per kilowatt hour. It's like really small. Now we're going to charge a floor, so everything just doesn't go to the ground. We destroy all value of these assets for power generation. So Dominic talk more about that. We'll sell power on a per diem lease basis. So we'll look at what typical usage is, calculate that equivalent amount on a per diem basis at about 5 cents a kilowatt hour, and then give twice the capacity, so to take care of demand, peaking, and interruption mitigation. Now my point would be, we have no moving parts. It's a very simple system, and it's made of things that should last indefinitely. It's much less complicated. I mean, in a relative basis, an airplane, like a jet, a 727 or something, it's much more complicated. But people trust it to get you over to Asia. You'll fly on that like 20 hours, and it probably has like 1 million parts. So I think this is going to be extremely reliable, and much more reliable than the grid, because we all experience grid outage, and that really sucks, because you don't know when they're going to fix it, and the grid is very, very complicated, and it's very expensive. Like this should be, we could just come out and give you another cell. I mean, when are you going to be there? Okay, go to the mall, we'll be there, we'll put the cell in. When you come back, it'll be all hooked up. So try doing that after Sandy. I think we were here, out like 2 weeks we didn't have power. So it's going to be better. Very reliable. So the cost is essentially the cost of the PV. You can see here the breakdown for this particular unit. We have the breakdown for all the systems, and this is the photovoltaic. Dominates the cost. So we really have to hammer down Massimo and get a better deal there. So all the other stuff's just a waste of time. You just got to get the PV in line. So this is a breakdown. This is a first of a kind 250 kW. This is if we went and bought all the parts, like out of a catalog, and it comes at $25,000, which is about $100 a kilowatt for just one of a kind. Then you get into mass production, it's going to get much, much cheaper. So addressing the PV, as long as you're in high volume, well, first the size. Once you're above 100 kW, of course you got to have all these electromagnetic pump and whatever, no matter what size you make. So once you're above a certain size, like above 100 kW, it's dominated by PV costs. That's the first thing. And then the second thing, as you go to higher suns, the cost comes down. So you're at $75 per kilowatt, and then of course the higher the volume, the more stuff you order per year, you get a volume discount. So you get 100 megawatt per year capacity, and you're like at $75 a kilowatt. And then if you go to like 10 gigawatt annual production capacity, then you're at $32 a kilowatt at 2,000 suns. And then if you go to 10,000 suns, which is like experimental right now, but in time it could get there, then you're so phenomenally cheap. It's way cheaper than anything you could fathom. So this is a basic design. We have the cell, inverter. These things here are readily available, and we have companies that'll do that. And I guess I should also say our model, and Dominic go into more of this, we're going to outsource everything. So we have contract manufacturing, contract supply chain management, we contract the installs. We got big companies lined up for that. They'll do preform pad. They say they can get it all permitted the same day, do the installations, do depot repair centers, do repairs, maintenance. We're just basically leasing as a business. So there's very little business risk on a relative basis. And then the inverters, we have companies that make the inverters. And then all this stuff downstream is known. There's another business that's actually pretty exciting. In addition to supplying power to telecoms, all these single power units, like there could be millions of them, and every imaginable device and home and factory and store, everything, everywhere you can imagine, even maybe eventually in gadgets like appliances, they could all be interconnected because we're going to have communication to and from to monitor how much power it's making, where it is, and to control it, and to do maintenance and track its current state of operation. So that can be the basis of a portal in and out for information besides information on the cell. So it can comprise a mesh network that could be an alternative to internet, for example. So that's another business that's feasible based on this. And it's on all the time. Like we'll run these power cells constantly, as we envision now. Say it's 100 kW rated, it'd be constantly 100 kW. And we'd dump power. I know that sounds obscene, but we would dump power, and you'd have instant on switching any kind of power level you want from 0 to its maximum capacity at any given time. So we actually made the pressure vessel much bigger so we could go up to megawatt scale, but it's actually pretty small in terms of equipment, comparable equipment. Like if you go megawatt scale in regular power generation, you're looking at something like half the size of this room. I mean, it's really, really big stuff. So this is going to be like small, like smaller than a small refrigerator. And here's some of the specifications. So it's going to be lightweight, like 100 kW or 250 kW. We can expand it just by turning the temperature up. It's about 200 pounds and about half a meter cubed. We're going to run the same kind of voltage they run from PV because it is PV. That's what's the beauty of it. We just basically take the same power conditioning and control systems as PV, same voltage, and we feed that into inverters, and we get out the same output as a photovoltaic. Proven technology, again. So our market is pretty much everything you can see with lights, and then secondarily, where there's no lights, this is ideal, where there's no grid. So we're reinventing electrification as autonomous, completely off-grid, mass-produced personal power. We do per diem lease, no metering, and we give cell redundancy because it's cheaper than doing any type of grid connection, so we avoid regulations in the process. And as I was saying, behind the meter, temporary learn-out, and then go off-grid with a global push. So this is the device, and I think Johnny's going to help me. This is what it looks like inside. He's going to help me go through here and show it, and then we're going to show a video of it operating. So this is the inside of it. You want to turn on camera? Yeah, let me turn. So you just go to something, I'll just kind of say what it is. All right, so first we have the black body radiator dome, and we have a seam here, graphite bolts, and we have a permafoil graphite gasket here. It seals it up. It comes in 2 pieces. So you can pop this off and do whatever maintenance. All this stuff is made to be quick assembled and for quick repair. Like the vacuum, or excuse me, the pressure vessel, for example, we can just pull that off. Everything else comes through the bottom. And their PV, again, would be in 2 sectionable halves, so we can pull that apart very quickly. Lift the pressure vessel dome off, and then we got access to everything. So here we have, this is one example of a design for an inductively coupled heater antenna. It's got cooling capability. Water runs through this conductor. So you can do both cooling and heating in terms of the system. So this would be retractable because once this gets up to 3,000 degrees Kelvin, then this antenna will not be able to withstand that types of temperatures. As I was showing in an earlier diagram, we have a oval type of coil that we drop up and down. So this is another type of retractable design for the inductively coupled heating, which uses a radio frequency power to heat up these reservoirs. There's 2 reservoirs, and inside there is a refractory metal electromagnetic pump tube, and then it goes into a nozzle that has a certain angle that makes it ideal for the two streams to intersect. These are screw-in, and then where these screw in, they're electrically isolated by zirconium oxide vapor deposit thin film coating. So you have electrical isolation between the 2. Basically, these replace the electrodes. So these are the injectors and the source of ignition current, and they're electrically isolated by a surface film that's non-conducting. So down below here, we have the electromagnetic pump. So there's graphite. Oh, again, this is all graphite. The surface on the outer part of that dome will be undergo a process called graphitization, so it has no sublimation. It's guaranteed as such. And this is a very, very special, high-quality kind of carbon. We have the machines and programs in here that we made all this in-house. We can make everything here in-house. We also have some supply chain manufacturers that we've already gotten some of these parts from, and they'll be able to make massive quantities very, very cheaply. So there's two connectors here. For the ignition system, we also have a way of jumpering these two across. So we run current through this electromagnetic pump connection so we can warm up this independently. So there's a way of warming up the electromagnetic pump section as we melt the silver with these radio frequency heaters. This dark object here is a heat transfer block. It's removed from the other side. You can just see the pump tube here with it removed. And that's a transfer heat from this base plate down to the electromagnetic pump section. So this melts the silver in this section so it'll flow and start pumping. There's permitted magnets here. There are things like cobalt samarium, or we could use neodymium as well, but cobalt samarium has better heat tolerance. And we have a fully integrated package with no connections, all solder joints that is very, very good for long duration, non-leaking and like, and then mount brackets. And then these magnets go vertically to the electromagnetic pump, and there's another set on the other side. They create an axial magnetic field. And then we have current tabs that you can probably see behind here that run current vertically through this electromagnetic pump. And then this is the base plate where all the feed-throughs go in terms of the power supply to the electromagnetic pump. The capacitor bank for the ignition system like is underneath this base plate. So once you pull this off, you've got access to all this. And then the housing panel underneath that, you would pull off and you'd have access to all the components underneath. So it's very convenient for quick breakdown and replacement of parts. I think it's good. So I think what I'll do, you want to hit the lights? This plays for about 13 minutes. What's that?
Will we have a chance to ask questions?
Yeah, in fact, what I'm going to do is this is this device running, and we have a portal hole in the top so you can see inside. So this is inside that dome. And as I said before, we had, let me just go back to me. So this is the injectors. So inside here are these refractory material riser tubes, and they have a nozzle, and they're shooting molten silver. And we're pumping it just so it hits this dome and runs back. So you're going to see this running back. Then we're going to turn up the pumping pressure so they intersect. And then we're going to turn on the ignition, and we're going to start the reaction. And it's got captions of when the ignition's on and when the ignition's off. And you'll see as this gets hotter and hotter and we get more vaporized material, it will run pretty much the same with and without ignition. And we're not even anywhere near the 3. We're probably getting up to around 2,500. But as we get up higher and higher in temperature, this will eventually get to the point where it'll be refluxing like a boiler in a steam boiler, but it'd be silver, and that'll give us massive electrical conductivity, so we can terminate the ignition. And you'll see we're already doing that now at these lower temperature regimes, and it's doing phenomenally well. So it looks like the only parasitic load we'll ultimately have is the electromagnetic pump, which is again very low power drain, and the creation of the hydrogen that's consumed in the process. And again, that's a very small fraction, less than 1% of the power put out by the system. So I'll take questions, and then you can follow the captions. It'll have pumping mode, and then we'll turn it up, and the two streams of molten silver that serve now as the electrodes will then intersect, and then we'll turn on the ignition system, and then we'll be turning it on and off during the run, and you can see the effect of the ignition system on and off in terms of how bright the device is. Brightness is actually really true. In other words, the camera is actually capturing, if you were there in person watching it, it's actually pretty good fidelity of what's going on. So, but one thing you will know, and I want you to appreciate, the reactor is not vaporizing because we're using refractory materials, and the electrodes aren't getting vaporized and destroyed. It's running. It should run in pretty much indefinitely, and as we perfect it, it will run probably the lifetime of the PV, which is 20 years. And the pumps, as I said, they're known. They're known technology in the field, operating 60 years maintenance free. Okay, so questions? Yes.
What's the longest you've been able to run continuously so far?
Well, we eventually shut it off because we got to go home. But yeah, maybe like 6 hours. But again, we're using. I'm basing this on how long it'll run, based on the parts we're using and in industry experience. And this pumping like this, 60 years maintenance free.
What's the output of that model?
We haven't measured the output yet. We just got the systems running, but the ones that Peter Jensen, Dr. Jensen's going to talk about, the validator, they're about megawatt scale.
Megawatts. That's going to
No,
be
this black body radiator, that's a good point. This black body radiator is made out of carbon. So carbon has a property called emissivity. That's sort of the amount of it's a measure of how much it'll emit or absorb light. The tenacity to do that. So this has the highest. It absorbs. You know how black things absorb light better than like white things. Like black asphalt gets hotter, then they have some white. It's not as hot. It's called emissivity. Emissivity is 1 for carbon, and the emittance at 3,000 degrees of a black body radiator is known physics. It's around 4.5 megawatts per square meter. So for this area of the dome we have, 6-inch diameter dome with emissivity of 1, this should put out somewhere around 330,000 watts of light, having a black body spectrum of a 3,000 Kelvin black body radiator. So that this dome would put out, we would run the reaction such that this dome would be at 3,000 Kelvin, so we would control that, and that would put out 330,000 watts continuously of light, and then the amount of electricity depends on what the photovoltaic efficiency is. And as I was saying, concentrator photovoltaic using sun, which is a different spectrum of ours, but sun is 42% in the field right now, and then we have light recycling. Now we're not going to get anywhere near that on first gen. We might get like 10. We use 2 junctions, maybe 20, but it'll improve with time. But it will be whatever that light output is times the photovoltaic efficiency would be the electrical output. Now we could turn that from 3,000 degrees Kelvin up to 3,500, and it doubles the amount of power. So rather than 330,000 watts of light, that would put out 660,000 watts of light, thereabout.
But your photovoltaic has got to be comparable to be able to absorb that light.
That's right. That's right. And that's going to take probably another generation, or we'll have to do standoff or something like that, or we'll have some reflectors to match what the PV concentrator can accept. But that gives another bar for concentrator PV, and people are pushing up to 10,000 suns now. So we'll see. But if we run it at 3,000, we're still going to be a little bit higher than what concentrators are now, so it probably has some light balancing we'll have to do, but that's nominally what it would put out at 3,000 Kelvin. That surface will put out 330,000 watts of light.
And your pricing baseline is all based on what you're telling us right now. So you're not, for pricing purposes, on a per kW basis,
Well,
that you talked about before.
That pricing is based on numbers we got from National Renewable Energy Lab and other sources of volumetric concentrator PV, what they projected a cost. So we're using numbers, basically government think tank numbers, and pricing the PV at those high volumes. So that would be at volumes of some like 100 megawatt per year and so many gigawatt per year volumes is where we're pricing in the PV.
I have a question about what I'm seeing here. These are two streams of what? Can you tell me what?
They're molten silver.
And they're both the same, or are they different?
No, they're matched pumps.
The streams, though, are they different metals, or are they?
No, they're both the same metal.
Same, okay. And then what, it goes to the bottom and just recycles back
Yes.
up?
There's two reservoirs, and they're electrically isolated from each other, so then when they hit, they ignite.
You mentioned sublimation.
Yeah.
Could you talk about deposits on the PV? Is there that problem's been solved?
Yes. I mean, we have two companies that they do a process called graphitization, and they said they'll guarantee for at least 6 months we won't get anything in the temperature range that we're projecting to operate. If you did have to clean it off, you would just pull the bell jar up, pop off the PV, clean the window, pop it back, and you're done. So, and then even if you look at expendable parts, the sublimation rate may be so vanishingly small, we don't expect that we'd have to ever replace the black body radiator, but even if you did, you can do the math. That's all carbon, and it could get phenomenally cheap. I mean, it could be like 10, 20 bucks for that. If it's that cheap, you're only looking at like an hour of running, and it'll pay for it. So, I mean, everything consumes something. I mean, cars, eventually they need overhauled and whatever the parts. But the parts are made so they're going to be super cheap. We can manufacture them in-house. There's ubiquitous amount of carbon. You can't exhaust the amount of carbon. In fact, we could take it out of the atmosphere and everybody would be happy about that. So we don't really see any problems with sublimation from what vendors. They even guarantee it's fine. They say we won't sublime until we go to 4,000. We're going to be at 3,000. Yes.
So how long after
Skip.
you hit ignition, how long before the black body radiator starts to glow at a level that you can capture
Oh,
energy
at that
from it?
temperature, the specific heat of carbon is very low. It should be very fast. I mean, it should be essentially instantaneous once reaction gets up to power. Because it's like a light bulb. When you turn a 300-watt light bulb on, like it just goes on immediately. You turn it off, it goes off immediately. Because it's picking up temperature very fast, and it radiates. The important thing is it radiates that power very fast. So when we turn off the ignition, it should, like a light bulb, it should just switch off immediately, and you see it's not. Yeah. And we're putting very low fuel rate flow in here. We got a lot. We can crank this up a lot in terms of power.
What is the internal pressure and atmospheric composition inside?
What's that?
What's the internal pressure and atmospheric?
This is running under vacuum.
Under vacuum.
This is running, yeah, these are vacuum conditions.
Does the UV damage the internal vessel at all?
No,
No?
that UV won't even penetrate a millimeter of air. There's some pressure.
There's some pressure.
Yeah, you couldn't do UV spectroscopy under these conditions. You'd have to go. This is on the like millitorr range pressure, thousandth of an atmosphere. You'd have to run down into the millionth of an atmosphere pressure for.
And there's no internal etching of the surface.
There's no what?
Internal etching of the surface. By
No,
the
no,
ion.
there's not. And in a commercial device, when we're up to temperature, it'll be like refluxing silver vapor, so that all the surfaces will be coated with silver. So it'll be like they say every dark cloud has a silver lining. We're going to have that phenomenon in our device as
Randall
well.
Mills. So I had another question.
Yes.
Just to make sure I understood it right. The silver streams have a proprietary catalyst in that liquid, is that right?
Right.
Okay.
And we can share that with validators. We share that with validators and
I just wanted to confirm that was what was
strategic
in-
partners. Like it's
Okay.
not a big deal.
Yeah, Randall, Jim Hansen, Longevity Capital, and a member of the Society for Classical Physics.
Yes.
After this reaction occurs, what happens to the hydrino gas? You mentioned that it permeates out. Does it actually permeate through the carbon, or where does it go? Where does it end up? And can you collect it?
Yeah, well, we have a gas collection system, and so we wanted to get this online, but we have done on the other systems, which we had open, like the one you saw at Columbia Technologies. We had that at Columbia Tech. We had that basically a system where we would have a gas line going into the side wall of the reactor, and it's an open reactor. and we'd be injecting some of this H3 argon-hydrogen mixture. Then some of the gas would flow through the gas line into a pre-condensing trap, which is a cryo trap at liquid nitrogen temperature, and condense out the argon, and then it would go into a charcoal trap and condense out the hydrino, and then we would then analyze it. And we get the Raman spectrum and the other spectroscopy we do to it to show we got hydrino gas. We actually get very good signatures. So now we're setting this up in a separate reactor, and we have a new hire that's really phenomenal analytical chemist to work full-time on characterizing the hydrino gas from this. Yeah, but you can. It does make hydrino gas. We've already shown that by a number of different spectroscopic techniques.
But you could recover the gas and actually use it for some purpose. I mean, as part of this, I mean.
Well, what we've done historically is we've captured it in some kind of matrix where the gas gets bound into the matrix. Like it either gets intercalated into the carbon, or it's bound into crystalline defects in the halide hydroxide crystalline mixture, where we actually not just physically mix them, we have to ball mill them so they're chemically mixed, and you get valencies or defects in there, and this hydrino gas binds in there, physiabsorbs in there, and we can look at it all these different spectroscopic techniques. So it's like when you do infrared spectroscopy, you put it on a sodium chloride, like a halogen crystal, that you put the material that you want to analyze spectroscopically, you put it on this transparent crystal, and the light interrogation goes through, and you can see the transitions in that material of interest. It's sort of the same thing. We have a crystal that doesn't have hydrogen, or in our case, there's no spectral signatures at all in that matrix material, but absorbs that gas, and that gas has its own characteristic signatures, namely an integer squared, and the integer being 16 times the energy of ordinary hydrogen. Okay, so now
It
it's just
sounds like you could do that, but I want a follow-up question to that.
so just repeating now, Luke.
But it sounds like you could do that, but what do you have to do?
Well, the only problem with
Doesn't
the
it have
gas-
a vent, like an exhaust pipe or something that this vents off into the atmosphere?
Yeah, it has no chemical reactivity,
So
so
there's
it's
no
vent
emissions
space.
issue from that stack.
But in terms of getting the gas itself, so we're chemically absorbing it into materials, and I didn't mention collecting the gas directly because it's going to be very difficult. Like, you know, have helium in like say you take Mylar and how helium will leak out. This is 64 times smaller volume. So if you imagine like a softball and like a grain of sand or something like that. I mean, it's so small that right now we're focusing on absorbing it into materials, and later we'll work on heating those materials and isolating the gas. We'll probably have to do some real-time spectroscopy, like online Raman and online other spectroscopic techniques, because of the high diffusibility of the gas. Okay, let me take one more question, then we'll get on to Dr. Jansen and get on with the rest of the program. Yes, one last.
Photovoltaic cell, where is that located? Is it inside the dome?
No, we don't have it on this device. It would go around this. We basically take triangles and make a geodesic dome of triangles to fit around the blackbody radiator. And it's modular scalable units, so we can make the dome bigger or smaller with the same components. So we can go, say, 100 kilowatts up to megawatt scale by using the same elements of the photovoltaic converter. Okay, thank you very much.